Welcome to lecture number 9 of my series Basic Mechanics, a Critical Look. In today's lecture, we will meet a new kind of physical entity which has been defined here. This is the cross product between two vectors r and p, the position vector and the momentum vector. The resulting vector is denoted by L typically, and this is called the angular momentum for a single point particle. Right now we are defining angular momentum for a given point particle. R, of course, is the position vector of that particle and P is the momentum of that particle. Both, of course, is being measured by some specific observer, and for the time being we are going to assume that the observer is an inertial one. Now, just from the geometry of the cross product, we can see that L vector, by definition, has to be normal to the plane containing R and P. So here you have a position vector for a point, and this is the momentum vector. L vector has to be directed perpendicular to both R and P, therefore perpendicular to the plane containing these two vectors, and according to the right hand rule, if you were to curl your fingers from R to P, then the thumb will point towards L, provided of course you are using the right hand. Also, the magnitude of L is given by magnitude of R times magnitude of P times sine of the angle between R and P. So theta here is this angle. Also, it is easy to see that mod P sine theta is nothing but this height of the parallelogram formed by R and P. So when you multiply that by the length of the base mod of R, you get the area of the parallelogram formed by R and P. So L is directed normal to the plane containing R and P, and its size, the magnitude, is essentially the same as the area of the parallelogram formed by R and P. Now, alternatively, there is another geometrical interpretation we can give to L, and for that we have to look at two successive positions of the particle in question. O here is the origin, P is the position of the particle at time t, and Q is its position a small amount of time delta t later. So this vector OP is R vector at t, and OQ is R vector at t plus delta t. The vector PQ, the vector joining the two, is obviously given by velocity of the particle times delta t. That's the displacement of the particle in time delta t. Now, if you look at the area swept out by the position vector in this time, that's the area of this triangle, OPQ. That's of course half the area of this parallelogram, OPQR, and from the same considerations that we had just used a while ago, the area of the parallelogram is nothing but the magnitude of the cross product between R and V delta t. So R cross V delta t's magnitude halved. Now you can take the delta t out of this and supply an extra m here. Of course I have to divide by m in that case to see that this is nothing but 1 over twice m times the magnitude of the angular momentum times delta t, the time interval. So the rate at which area is swept out by the position vector, area in time delta t divided by delta t, so-called areal velocity, is actually essentially magnitude of the angular momentum vector up to a factor of twice m. This is something which is going to come in very handy later on. Now, because we are dealing with mechanics, one of the major questions that we should ask is how does this quantity L that we have defined now change with time? How fast does it change? To do that is a matter of simple calculus. You differentiate L with respect to time, you get d dt of L, that's of course d dt of R cross P. And now we use the standard result that when you are differentiating a cross product of two vectors, you can essentially proceed in the same way when you are differentiating the product of two functions. Remember, when you are differentiating u times v, that is, you are calculating ddt of u times v, u and v being both functions of t, the result is du dt times v plus u times dv dt. That's exactly what you can do here as well. This differential is nothing but dr dt cross p plus r cross dp dt. The only thing we have to be careful about when dealing with the derivative of a cross product is the basic idea that cross products do not commute. So when you are doing dr dt, it has to be the first factor, and when you are doing dp dt, it has to be at the same position as p, that is, has to be the second factor. Switching the order of these would give you the wrong result, unlike the case when you were dealing with products of functions. But now dr dt is simply the velocity. So the first term is velocity cross momentum. The second term is r cross dp dt, which of course is the same as r cross f, where f is the force acting on our point particle. Remember, we are assuming at this stage that the observer involved is inertial. So Newton's second law holds for that observer. dp dt is the force. Now momentum p is simply mass times velocity. That means v and p, these two vectors in the cross product, are parallel to each other. The angle between them is 0. That of course means that their cross product vanishes. So we are actually left only with r cross f. And we denote this quantity, the cross product of the position vector with the force, by tau, and call this a torque exerted by the force. So this equation can be just stated in words as follows. The rate of change of the angular momentum of a point particle is equal to the torque acting on it. The torque tau is nothing but the cross product of r and f. It has a magnitude given by mod of r mod of f times sine theta, and is directed perpendicular to the plane containing r and f, and its sense is described by the right hand rule. Now, an immediate corollary of this law is the following. If torque acting on a particle were 0, then its rate of change of the angular momentum would be 0, and therefore L would be conserved. It would be something which does not change with time. So the particle can move, its position will change, its momentum might change, but r cross p will not change as long as there is no torque. This is the law of conservation of angular momentum for a point particle. In the absence of torque acting on a particle, the angular momentum of the particle is a conserved quantity. We will now take a look at a few examples and try to understand this in some detail. Our first example may seem a bit counterintuitive, especially the name of the quantity, angular momentum, seems to imply that angle is involved somewhere in its description, and basically it tends to give us the impression that this is something which will be more relevant to motion where the angle changes, situation like a circular orbit. Our first example, however, will be simply that of a free particle. A particle which moves, of course, with uniform speed along a straight line, one whose velocity is a constant. Remember once again that we are assuming that this is an inertial observer who is doing the observing. So the free particle, a particle on which there is no force, will move with 0 acceleration. Now, according to our result that we had proven a while ago, on a free particle, the torque of course is 0, there being no force. R cross F has to vanish, and therefore L must be conserved. As I have already stated, the notion of angular momentum is not the first thing that comes to our mind when we are talking about straight line motion, especially free particle motion. Let's see how that works out. Here O is our origin and A, B and C are three successive positions of the particle at equal time intervals. So a time interval of delta t has elapsed between A and B, another delta t has elapsed between B and C. So of course AB and BC have exactly the same length, because the vectors denoting them are exactly the same. They are both V delta t, or R2 here. This position vector, the position vector OB, is the same as R1 plus V delta t. Of course, R3, the position vector of C, would be R2 plus V delta t. Anyway, right now let's look at the angular momentum of the particle when it's at point A as opposed to when it's at point B. At point B, the angular momentum would be L2 given by R2 cross the momentum. The momentum doesn't change, it's mv at both A and B. So R2 is R1 plus V delta t crossed with mv. Of course, it's split into two pieces, R1 cross mv plus mv delta t cross V. And here mv is parallel to V, the same argument that we used a while ago, and this cross product vanishes. So we are left with R1 cross mv, simply L1. Geometrically speaking, the direction of the angular momentum is the same at A and B. That's very easy to see because at A, the direction is a normal to the plane containing the triangle OAB, and at B, the direction is normal to the plane containing the triangle OBC. And OAB and OBC are of course in the same plane, so the normals are in the same direction. What about the magnitudes of angular momentum? Remember, the magnitude of the angular momentum, as we have just worked out, apart from a factor of m, is essentially double the area of this triangle OAB, that's for the point A, and point B is double the area of the triangle OBC. Now these two triangles are very different, but they have the same base. AB is the same as BC, and if you drop a perpendicular from O onto the straight line, that gives a common height to both of these triangles. So both of these triangles are the same height, namely this much, and equal bases. Therefore, both of these triangles have the same area, and that's of course what is related to the angular momentum of the particle at A and B. So geometrically, we can see that the angular momentum does not change when the particle moves from A to B. And here, of course, A and B are any 2 points on the path of this particle moving in a straight line with uniform velocity, this free particle, and therefore the angular momentum is definitely conserved here. The next problem also involves rectilinear motion along one straight line, one-dimensional motion. But now we do not assume that this is a free particle. There could be a force acting on the particle, but the force would be along the direction of motion, and so would the velocity be. Now here, torque of course is not zero in general, because F is not zero and the position vector in general of course will not be zero. The particle is not sitting at the origin. However, if we choose the origin on the line of motion, so the particle is moving along the straight line, we put the origin here. The particle is somewhere here. The force acting on it, F, would be along this line. The position vector would simply be this vector, again along this line, pardon my drawing there. And so R and F would be parallel, and therefore R cross F would vanish. So zero torque, angular momentum should be conserved. While this result is correct, this is rather trivial, because for this motion, as long as you put your origin on the line, R is along the line, the velocity has to be along the line, so R cross V is zero trivially, because R and V has to be parallel vectors here. So angular momentum in this case is simply zero throughout. So the fact that it is conserved is definitely true, But something which is zero throughout being conserved is really not that interesting. But let me point out one thing. Even in this simple situation of a particle moving in a straight line, the conservation of angular momentum, trivial as it may be, works only when you put the origin on the line itself. If the origin were away from this line, then torque would not vanish, angular momentum in general would not be conserved. The third example that we are going to discuss fits in more closely to our notion of angular momentum as something which describes angular motion or circular motion. This is a particle in uniform circular motion. Now, as we all know that in such a situation, if the particle is somewhere on this circle, the velocity will be along the tangent that is perpendicular to the radius, and the force acting on it will be directed always towards the center. This is uniform circular motion, where the acceleration of the particle is always directed towards the center, the so-called centripetal acceleration, and the force acting on it has to be thus directed towards that point. Now, in this case, you do have a force. The velocity is changing with time, although the magnitude isn't, the direction is. So there is an acceleration and the motion is not force-free. However, because the force is always directed towards the center of the motion, if I were to put the origin at the center of the circle and only at that point, would R cross F vanish at all points along the path? R would always be parallel to F. So, under such a choice, only if you choose the origin to be at the center of the circle, torque is zero throughout the motion, angular momentum L would be conserved. Now here, once again the direction of L is simply the direction which is perpendicular to that of the plane containing R and V, and since the circle is planar, R and V are always in the same plane as the plane of circle. So the direction of L being conserved is rather trivial. It's always directed in this case towards the normal pointing out from the plane, pointing out towards you. So that's the direction of L. But what about its magnitude? L is m r cross v. So its magnitude is simply m, the mass, times the magnitude of r cross v. Now for uniform circular motion, indeed for any circular motion, r and v are perpendicular to each other, and therefore the magnitude of their cross product is simply the product of their magnitudes. It would have been mod r times mod v times sine of the angle between them, but the angle between r and v in this case for circular motion is 90 degrees or pi by 2 in radians, and the sine of that is 1. So here the angular momentum is simply the momentum times the radius, mvr. And since the motion is uniform circular, r of course doesn't change with time, neither does v, the magnitude of the velocity, and therefore mvr is definitely constant. So this fits in with our finding that here L vector has to be conserved because torque is 0. The magnitude of L is mvr, which is constant, and it's always directed perpendicular to the plane of the circle. Our next example will again involve circular motion, but this time we will talk about non-uniform circular motion. The particle is moving in a circle, however its velocity, not only is its velocity changing with time, as it always will in the case of curvilinear motion, but the magnitude of velocity, that is the speed, is also changing with time. Now, as in the previous case, velocity will be along the tangent, and its magnitude v is given by the angular velocity into r. The only difference from the previous case is whereas in the previous case the speed v was a constant, therefore omega was also a constant. Now v, the magnitude of the speed, varies. Of course it varies along with omega in direct proportion to it. Now once again the direction of L vector is simple. is directed perpendicular to the plane of the circle. The same argument, this is r vector, this is velocity, and r cross v will be perpendicular to the plane containing both r and v, which is the plane of the circle. Magnitude of L, as again, is simply given by mvr. Once again, the velocity and the radius vector are perpendicular to each other, one being along the tangent to the circle, the other being along the radius. Of course, once again, what you have done is place the origin at the center of the circle. And since v is omega r, this result is the same as m omega r square. Now, the direction of the angular momentum doesn't change here. But the angular momentum can, because in this case, the magnitude of the angular momentum is not a constant. Remember, v varies with time. So, mvr varies with time. And the rate at which the magnitude of the angular momentum changes with time is simply m times dv dt times r, or dv dt, the rate at which the speed changes. Note that this is not the rate at which the velocity changes. It's the rate at which the magnitude of the velocity changes. Is simply given by d omega dt times r, and d omega dt, the rate at which angular velocity changes, is given by the angular acceleration. So m times alpha r times r, so m alpha r square. And in this formula, of course, alpha is the rate at which angular velocity changes with time, something which we call the angular acceleration. So this is the angular momentum, its value as well as its rate of change. Now what about the torque? Well, to figure out the torque, we have to calculate the force acting on this point particle and take r cross that. To figure out the force, we need to first worry about the acceleration and multiply that, of course, by mass. That will give you a vector which is equal to the force acting on the particle. Here, the acceleration, unlike in the previous case, will have two components. The radial one is still inverse, it's the centripetal acceleration as always, and its magnitude is given by plus v square by r. The minus sign here simply is there to denote that it's actually inverse. It's not in the outward radial direction, but in the inward radial direction. In addition to that, for non-uniform circular motion, there is one more component to the acceleration, a component along the tangent. And it's this acceleration component which is given by r times the angular acceleration, r alpha. Now I admit that we have not discussed circular motion in this series so far, but I am pretty sure these are results which should be familiar to you from whatever you have studied about circular motion in school. In general, if you have uniform circular motion, the acceleration is directed entirely towards the center. That's the so-called centripetal acceleration. But when you have non-uniform circular motion, the acceleration is actually not directed towards the center. Is directed at an angle with an inward component given by v square by r in magnitude and a tangential component given by alpha r. Of course, for uniform circular motion, alpha vanishes, so this tangential component is not there. Now, the force, of course, will also have two components. The radial component will have a magnitude of m times v square by r. This is the so-called centripetal force that we talk about all the time. And the tangential component of the force will be given by m alpha times r. Mass times the tangential component of the acceleration. So here also the force will be directed at an angle. We'll have two components, Fr and Ft. Now when you take the cross product of this with r to find the torque, note that r is parallel to the radial component of the force. So if you write F as Fr, the radial component, plus Ft, r cross F will be r cross Fr plus r cross Ft. But r cross Fr has to be 0, both vectors being in the same direction. So it's just r cross Ft. And because r and Ft are two vectors which are perpendicular to each other, one being radial, the other being tangential to the same circle, the angle between these two vectors is 90 degrees. So the magnitude of the cross product, the magnitude of the torque, will simply be length of r vector times length of the vector Ft. So that's simply given by r times mr alpha, mr square alpha. And since it's r cross f, this vector r crossed with the vector f, it's also directed normal to the plane containing r and f, which is the same as the plane of the circle. And you can easily figure out using the right hand rule that the sense is the same as the sense of the angular momentum. And what about the magnitude of the torque? We have just shown it's mr square alpha. And just a while ago, we had proven the rate at which the angular momentum's magnitude changes is also given by m alpha r square, exactly the same quantity. Note that L vector here has a constant direction, so its rate of change is essentially in that direction, and its magnitude of the rate of change is the same as the rate of change of the magnitude. This is not true in general for vectors which change direction. The change in the vector cannot be captured only by the change in the magnitude. But for vectors which are in the same direction, you can always use d dt of magnitude of L is the same as magnitude of d dt of L. And that is exactly what we are verifying here. Rate at which the angular momentum changes has a direction and a magnitude, both of which exactly match that of the torque. So we have verified dl vector dt equals torque vector, at least for this particular situation. Our final example is going to be a lot more non-trivial than this. We will actually have a lot more to say about this example later on once the course progresses. And this one is the situation of a particle under what is called a central force. Now, what is a central force? A central force is a force which is always directed towards a fixed point. So, as a particle moves in its path, which is shown by this blue line here, the force acting on the particle is always directed towards this fixed point, which let us call that O for the time being. This fixed point is called the center of the force. So when the particle is here, the force is like this. When the particle is here, the force will be directed like this. Again, directed towards O. When it's here, it will be directed like this. Now, this is a rather special kind of force we talk about. But the reason why this is so important is that there are many very good examples of this. For example, when a planet moves around the sun, the force of the planet is always directed towards the sun. Now, in a planet-sun system, both the planet and the sun attract each other, and as a result of the joint attraction, both the planet and the sun move with respect to an inertial observer. They are both acted upon by forces, so they are not acceleration free. So although it's true that the gravitational force between a planet and a sun always points towards the sun, it is technically not correct to say that this force on the planet is directed towards a fixed point. The sun is not really a fixed point, at least not according to an inertial observer. However, although the sun does move a bit because of the huge mass of the sun, the motion of the sun is actually very small. And if you assume that the mass of the sun is infinite, as we have done here, then the sun would not move at all, and the force on the planet would be truly a central force. We will learn later how to take into account the fact that the sun actually moves a bit and how that modifies the sun-planet dynamics a bit. But that we will talk about later. Again, the force on an electron due to the nucleus of an atom is always directed towards the nucleus, and the nucleus is way heavier than the electron, so you can at least at a first approximation treat that as stationary. So in both these very important situations, you have a force directed towards a fixed point. Let me repeat once again. This fixed point is called the center of the force. And here, the force changes in direction, in magnitude, but always keeps on pointing towards the same point. So an obvious choice for the origin would be this center of force. point towards which the force is always directed. Towards, if it's attracted towards the center, or it could be away if it's repulsive, or could even be a mixture of both. At some part of the trajectory, the force could be towards the center, at some other points it could be directly away from it, but always along that line joining the particle and this fixed center of force. So if your origin were placed at the center of the force, which I have already suggested by calling the center of force O, then R vector would be the vector joining O to the position of the particle. And that will of course be parallel to F, either making an angle of 0 degrees if the force were repulsive, or 180 degrees as has been drawn here, where the force is attractive. In both cases, sine of the angle between R and F is 0, and therefore R cross F vanishes. So this is a situation where the angular momentum, as measured by the observer fixed to the center of force, is a conserved quantity. Torque vanishes, L is conserved. But this actually has far-reaching consequences. One immediate consequence of this would be the direction of L does not change with time. After all, if a vector is conserved, then it's conserved in both magnitude as well as direction. And the direction of L definitely is the direction of R cross V. That is, it's perpendicular to the plane containing R and V. Since L has to have a fixed direction, this plane containing R and V, or equivalently R and displacement, the change in R, must stay fixed. And therefore, the planet's orbit around the sun, or the electron's orbit around the nucleus, if you could treat that using classical mechanics, which you can't really, but that's another story. Or in general, the motion of any point particle under a central force must be planar. The particle is always confined to a plane, despite the fact that the situation is actually three-dimensional. We can see that the situation is three-dimensional because if you were to change your initial conditions, the plane would change. The initial plane, formed by the initial value of the position vector and the initial value of the velocity vector, is the plane to which the particle has to stay confined. That of course can be changed by changing the initial conditions. But once that is fixed, the plane in which the particle moves has to be a fixed one. So orbits of particles under central force field are always planar. What about the magnitude of L? Now this is where we will use the geometrical interpretation, the second geometrical interpretation of the angular momentum's magnitude. The magnitude of L, as we worked out, is actually twice m times the areal velocity, rate at which the radius vector, or the position vector basically, sweeps out area. Now this is conserved. Since L is conserved, its magnitude is. So areal velocity is something which does not change with time. And that means the radius vector, the vector joining the origin to the point where the particle is, the position vector in other words, must sweep out equal areas in equal times. Now if this sounds familiar to you, it should be. This is the famous second law of planetary motion due to Kepler. In fact, Kepler's first law says the planetary orbits are ellipses, which are of course planar. The second law says that not only is the motion planar so that L's direction is fixed, its magnitude must also be fixed. That means Kepler's second law, when you apply mechanics to it, tells you that the angular momentum must be conserved. So torque must be zero despite there being a force. And the only way that's possible is that if the force is central, always directed right towards the fixed position from which these areas etc. are being measured. That actually is the position of the sun. So as you can see in this picture, O is our center of motion. A, B, C are three successive positions of the particle at equal time intervals. And what this essentially says is that the area swept out by the position vector from A to B, that is the area shaded here, roughly the triangle bounded by O, A and B, is the same as the area of the triangle bounded by O, B and C. Note once again that Kepler's second law really is a consequence of the force being central. Does not have to be the gravitational force. Any other central force field will also lead to this particular law, the area law. To finish today's lecture, let me point out that from the two laws of Kepler, Kepler's first law, which said that the orbit of a planet around the Sun is an ellipse with the Sun at the focus, hence a planar orbit. And the second law, equal areas are being swept out by equal times by the radius vector. Newton could figure out that the force is central. Kepler's third law actually told him that the force had to be inverse square. Exactly how Kepler's third law led to Newton concluding that the force between the planet and the Sun obeys an inverse square law, falls off in magnitude in proportion to the inverse square of the distance, is an altogether different story. We are going to talk about that sometime later in this series of lectures. But for the time being, let me point out that once Newton could figure this out, that the force is central and that is inverse square, from that he could figure out something rather sweeping. The orbits of planets around the Sun must be conic sections. Figures you get when you cut a cone by a plane. For planets you had elliptical orbits, but you could also have open orbits like the parabola or the hyperbola. So planets, comets, everything could be explained by one of the greatest triumphs of science ever. Angular momentum and its conservation lies squarely at the heart of one of the greatest scientific revolutions of all time, the discovery by Isaac Newton of universal gravitation and its consequences. At that note, let me call it quits today.